ठीक है, Bismillahirrahmanirrahim. So in this first lecture we are going to talk about distributions. There are 3 or 4 different types. Distributions is the main concept of statistics. Everything is based on distributions. Basically in data analysis there are numbers, 5, 8, but in statistics and probability there are random variables, and the random variables are everywhere, and a random variable is nothing more and nothing less than a distribution. And what is a distribution? It is the set of values over which the random variable can vary. So it has a minimum value and a maximum value and a range of values, and in some of these values are more likely than others are less likely. So this is the general idea, but we want to make it very specific and concrete. So the simplest concept is data distribution. Data distribution there is no randomness, there is no random variable, but it becomes later on the basis of a random variable. But it's the easiest to understand. So we will start with the concept of a data distribution. It's about purely a fixed set of numbers. So let's look at this is a data distribution of the HISE, Household Income Expenditure Survey data. Now this is the distribution. What is the distribution? The blue curve. This is telling us how many people there are in what range. So actually there's the whole data is about 15,500 people. All of the people reported their incomes, and the income ranges from 0 to this big number. This is 101 million or something like that. So this is the distribution. It tells you how many people have how much income. Now actually this is not a very good picture. I want to go to L2 data. इसमें ये HISE data है. This is the HISE data set, and these are the incomes that we are plotting. Actually the first one is the household code, then we have province, region, this is the sampling unit, this is the household size. I don't know why they have repeated it in 2 columns. So in this household, which is actually identified where it come from, province 1 has, there is a separate file which tells you province 1 is, I don't remember what it is, Punjab or Sindh or some Balochistan. And then region, the region also is specified, Ladkana hai, kya hai. And then the PSU, which is the sampling unit. And then there are 5 people in this household which were sampled, and their total calories were 10,850, and their annual income was 24,000, and their total expenditure was 120,000. How did this happen? Well, probably they used up some of their savings. Anyway, this kind of thing can be a problem. So anyway, इसमें जो है, what we can do is sort this. Custom sort by total income. Income is not a good variable to sort by, but let's just do that. So it says sort in values, order smallest to largest, and now I'm going to click OK, and here it is. See, the data has been sorted. The total income is now starting at 0, and we can go down. This is 15,510 entries, and the biggest entry is 10 million. And now what is the distribution? Well, basically in distribution what we do is we divide the data into categories, and that is called bins. So we can say 0 to 1,000 is one bin, 1,000 to 2,000 is the second bin, 1,000 to 2,000 to 3,000 is the third bin, and so on. And then we ask how many people are in this bin, and that is what the histogram is, and that is the picture of the distribution. So now we go back to the picture. So this picture is not very good. I mean, we can't see what's going on because there is an outlier in this. It's very important to learn. So there is this 100 million person, and he's at the bottom end, and because of this presence of this, so all of the data is compressed. Most of the people have income between 0 and this 4 lakh, sawa 4 lakh. That's the most where the most of the data is, but it's only being taking up very small part of the graph because we are putting in all of the data. So the way to solve this problem is to chop off the outliers, and that's what I have done here in the next slide. So here I went to 0.3 million. So now we can see more clearly something about. So these are bins. I don't remember. I think this is bin of size 2,000 each, or maybe it's 4,000 each. Now this is actually not a very good looking histogram. In a good looking histogram you don't have this kind of fluctuations ke upar ja raha hai phir niche ja raha hai. This is indicative of a rounding off pattern, because what happens is that so the round numbers are getting more people in there, and the in between numbers are not getting less. That's why this histogram is not very smooth. But anyway, in each bin you have the number of households. So for example, if you look at the biggest point over here, there are 750 households or something like that, which have incomes between 66,000 and 68,000 or something like that. So just like that, each of these bars is telling you how many households in that category. And actually this is one of the, in your exercise you will be making histograms and studying them, and I'm going to make some in this lecture as well. So in order to visualize the data, we have to make a histogram for it, but there are many. Histogram is not actually unique. There is no one best histogram for the data. There are many things that you have to do to make a good histogram which allows you to see the data. One of them is to truncate the outliers. If there are a few numbers which are very big, they are going to compress the graph, and you're not going to be able to see the picture, so just get rid of them. Here, for example, even in my previous picture, this scale is too big. Probably if I went up to 192,000, I would get a much better, cleaner picture, and then I could make my bin size smaller. So you can make bin sizes 0 to 10,000, 10,000 to 20,000, and if you did that, what happens is that if you make the bin size too large, then a lot of data falls into one bin, and then you can't see what's happening. If you make it too small, that's also a problem, as we will see, because every data then falls into one bin, and you can't again see the patterns in the data. So choosing the right size of bin is not at all an easy problem, and in fact the current consensus is that you should make the picture with many different bin sizes, and then you will get the idea of many different kinds of patterns. So in order to visualize the data, you have to choose the bin size and to make the histogram, and you make the histogram with different bin sizes to get some idea. One problem that arises is that the bin size is not fixed, in the sense that for poor people a small bin size is good, like 0 to 100, 100 to 200, because there's a huge number of families. We have 15,000 families, maybe 10,000 are falling between the area of 0 to 10,000. So here the bin size can be very small. For the very rich families, there are only a few families, and so if you make a bin size of the same 0 to 100, there will be nobody there. what you need to do is to make a large bin size for so the bin size itself can be variable and should be variable. So one way to avoid variable bin size is to change the scale of the data. I haven't done this in this exercise. If you take the log of the numbers, instead of plotting the income, if you took the log of the income, then that compresses the larger values into a smaller scale. And so that's one way. And this is explained in more detail in my Introstat lectures, which are available. And actually I refer to them. The thing is that I don't have time to cover all of the background. This is an applied econometrics course, and so statistics, mean, median, mode. I am assuming knowledge of elementary graphical techniques and so on. But actually the way I cover it is different from the way it's covered in the standard courses. And all of this material is available in the Introstat course, which is available online, and you can watch the lectures and read the materials and do the exercise whenever you need. If you have need to clear some concepts which are background, then you should go back to that. Similarly, the Excel exercise that was done last time was also a background material. So I asked about Amna and about the report from the exercise, and she said, okay, I was able to do the first two. The third part, the student said, okay, because the time was over, that we will do it next time. So one thing you understand is that no next time. I mean, you will do it yourself. It's not, if the lab is only there, it's not a class. It's meant to help those students who cannot, and students who need a little bit of a helping hand. So you ask her for any problems that you are having, and if you don't ask, then you do it on your own. It's not we are going to, whatever was done was done. The next class will be on current material. We will go at the pace that is in the class. Alright, so we go on to the next slide. This is the infant mortality histogram. Now let me do this. So I'm going to try to show you how Excel does this. Now we go to the infant mortality data. That's over here. This is the infant mortality in 2010. Now, I have done a couple of things. First of all, this is the original data, which is coming from the World Bank data series, which is available on the internet. It has data on a lot of all countries and a lot of different variables. So this is the infant mortality original data. Then what I did was, so this is the country name, this is the country code, 3-letter code, this is the indicator, which is mortality rate infant per 1,000 live births. This is the name of the data, sp.dyn. This is the World Bank code name for this. And then this is the data 252. What does this mean? It means in Afghanistan in 1960 252.7, 253 children out of 1,000 children died in the first year of birth. This is a very high mortality rate, 1/4 of the children. In Algeria, this same number was 146, and in Belgium it was only 30. So there is a lot of differences, and there are blanks in the middle, which are countries for which we don't have the data. Now what I did in order to simplify things was to look at the recent data, 2010, and I just copied this column onto the next sheet, and I copied the names of the countries and the codes of the countries. And this is something that you should have learned how to do basically in Excel, so I'm not going to repeat this. Now, after copying them, I did a sort, just like we did the sort. So in the sort from lowest to highest, we find that San Marino has the lowest infant mortality in the world in 2010 with 1.7 deaths per 1,000 children. Iceland has 1.8 and so on. Singapore is pretty good. Now, I want to do is to make the histogram. So, in the histogram, one way to do it is to ask Excel to make it for you, and this is what I have done here. I asked Excel to make it for me. What you do is you go to data, and then you go to data analysis, and then you go to histogram. Okay, now it asks for the input range. What is the data that you want to make the histogram for? So I will tell it about this, and then I go here. And now, oops. This is going from C2 to C226, but actually I only want to go to 224 because that's the last country. At the bottom I have the average and the standard deviation, which we will use later. Okay, so this is going from C2 to C24. And now the bin range. Now that's where, if I don't specify the bin range, then Excel chooses bins for me by itself. It looks at the data and decides what is a good. And now, if I ask it to I want to click on the chart output, and I will say OK. So one thing I have done is to let it go to a new worksheet ply, which means that it will create a new sheet. So now if I press OK, here it is. So it chose the first bin at 1.7. There is exactly, so there is one country. The frequency 1 means that there is one country in this bin. What is this bin? This is less than or equal to 1.7. There is only one country. And then the next bin is 1.7 to 10.21429, basically 10.2. And so in this range there are 67 countries between 1.7 and 10.2. And then the next is from 10.2 to 18.7. Basically it is making bins of size 8.5. The bin size is the fixed, but it has chosen the first bin to start at 1.7. And it has chosen the bin size to be 8.5. And so now this is the bin, and each bin, like 18.72, means that there between 10.2 and 8.7 there are 46 countries. In the last, at the end of this, at 112, there are 3 countries, and there in the more category there is one country. There is one country which is even worse than 112. Now, suppose I want to choose my own bins, which is what I would like to do. So then I have to provide Excel with numbers that I want for the bins. So I can start with, let's do something simple like 10, 20, okay, so 110 and 20 तक ले जाते हैं इसको. Okay, so I have set up my bin sizes, and now I can go into data analysis and ask for a histogram, and the countries are correctly stated. So all I want to do now is to specify the bin range, and the bin range is going to be this one. Okay, so it's E20 to E31. That's the place where I have my bins. And now I'm going to keep it on this sheet. So then I have to put output range. Where do I want this output? So now I can say I want it in G20. Okay, so now it's going to put the output into this sheet. And that's it. Okay, so now you see it has made the graph for me. And this is what the histogram looks like. There are about 68 countries in the first bin between 0 to 10 and 54 countries in the next bin. And this picture is the distribution of the data. Now, one thing to understand is that this is not unique in the sense that as I change the bins, they are all distributions of the data. Any histogram is a distribution of the data. So, distribution is not uniquely defined. Okay. I can make the bin size smaller, 0 to 5, 5 to 10, and so on, and I will get a different picture according to the size. Now, what I want to show in the next graph, basically I calculated the mean and the SD of this data. You know about these things, I hope. And the way to do it is very easy in Excel. Here, if you look at the bar, it says equals average C2 to C224. That tells you what the average is, and that's 29.2. So the average infant mortality is 29.2, and the standard deviation is also calculated like this: equals STDEV C2 to C25. Acha, that's a little bit of a trick. Anyway, it doesn't matter. Basically, it would be the same for C2 to C24. So anyway, the standard deviation is 27.3. And now, the important thing that I want you to understand is that standard traditional statistical data analysis is based on just these two numbers. Instead of using the whole data, we use these two numbers, and implicit in this is the idea that the data is normally distributed. So if we make infant mortality data on the basis of the assumption that it is normally distributed, then it would look like this. This is what the distribution would look like if the infant mortality was normal. That is the red bars. And nearly all of the analysis you do in regression and statistics is based on the assumption that the data is normal. So basically, even though the actual data is the blue graph, the conventional statistic analysis is based on the red graph. And as you can see, there is no real match between the two. So most of the conventional analysis is basically wrong. And that's why we are trying to do things in a better way. Here is another graph of the GDP per capita, which I have the data here also. That's the GDP per capita. This is the original data, which is in the World Bank series. Then I think in sheet 4, I have copied the data for 2010 only, and then I have made a graph for this, exactly like I did before. Here I let Excel choose the bins. So it shows the bin to start from 138. And as you can see, there are a lot of poor countries and a few very rich countries. Because of the way that this is scaled, you have 127 countries falling in the first bin. So this is not a very good graph. Actually, what one would this is one distribution, and what it shows is that there is a huge bar. So in the if you look at the distribution of the income, the GNP per capita, then you can tell from this graph that there is a lot of very poor countries between 0 and 4,600, and then a few. Then basically the number declines sort of monotonically. So 127, then in the next category you have 30, then you have 11, then you have 7, 6, 10, 5, 6, 1. So it becomes smaller and smaller. So you have, this is called a left skewed distribution. It is not a symmetric distribution. Skewed because you have a few very rich countries very far away from the center. But you don't have a few very poor countries in the sense that you at 0 you finish, so you can't go, to the negative side, which is what you would need to make this graph symmetric. So there is a few very rich countries, but most countries are poor. This is what the distribution is telling us. Now actually, if we wanted to make a better distribution, we could truncate. We could get rid of, for example, we could go up to about 30,000. That covers the last big peak. Or we could go up to 40,000. This is over here. And 40,000 के बाद सिर्फ एक country है. So if we go up to 40,000, and then we could make the bins smaller, 0 to 1,000. If we make the bins smaller, then what is happening in the poor countries would become much clearer. So this is the data distribution. Now we have to cover some more concepts. Started at 12. I'm supposed to 1:30, right? Okay. So one thing that I've already pointed out is that normal is a bad approximation to most data sets, but nearly all of conventional statistics and conventional econometrics is based on the assumption that everything that you see, all random variables, are normal. Why did this happen? There is a reason for this. The reason is that in the olden days, when this all statistics was being invented and econometrics was being invented, there were no computers. Even in 1970s, when I was studying in MIT, and we were told to run a regression, we were actually given a budget in the lab that I have $100 computing budget, and running one regression was like $3 or $4 worth of. There was so running one regression was a very difficult job. Now you can run thousands of regressions without any cost. So doing this kind of analysis that I'm doing was impossible. So basically, the normal distribution makes the calculations very easy, the easiest possible. So that was the only thing that was possible at that time. So everybody assumed that, because if the data is not normal, then there's nothing you can do. You cannot do the analysis. The computing power is not available. So that's why that was built in. And now momentum, inertia, because it was done that way, and there's a huge amount of theory that has been developed, and all textbooks have been written. So this assumption that everything is normal has been buried. There are Nobel Prize winners who ran a hedge fund, a stock market company in the USA, and they assumed that the stock returns would be normally distributed, and for a while they made huge profits, much better than anybody else. But then one day they had a huge collapse. It was so big that billions of dollars were lost in one day. And so basically this is the real data tends to be, especially stock returns, approximately normal most of the time, but like 90% of the time. But about 10% of the time you get huge outliers, and those outliers can destroy the normal distribution, and basically they caused a collapse of that firm. And so assuming that things are normal can be quite dangerous. So alright, so this is the summary of the material up to now. when you want to create a data distribution, you have to subdivide the range of outcomes from the minimum to the maximum into bins. Bins has to be carefully chosen. You can actually make the bin size variable, but Excel is not equipped to make a graph of the histogram when the bin size is variable. It doesn't make the right graph. So if you, the reason is that basically in the histogram, the area of the graph, yani, should represent the data. Yani, the bar size should reflect the proportion of the data in that bin. So if you make a bin size large, now the way Excel makes it is that whether the bin size is large or small, if there are 4 points in it, the bar is at 4. But actually, the way it should be done correctly is that if the bin size is very large and there are 4 countries in it, then the size of the histogram should be reduced, because the area of the square should represent 4 and not the height. In the Excel histogram, the height represents the number of countries, but actually that's not the correct histogram. I will get to that later. Yes, in fact, this is explained here. Basically, what we have plotted so far is called the count histogram. In each bin, you put the count of the number of countries. But this is not a good histogram because it's not comparable across countries. Suppose that in the first year, in 1960, data is available only on 120 countries. And in 2010, data is available on 240 countries. So a lot more data is available. So now if we make, and suppose that the income distribution is exactly the same, then if we make the graph in 60 and we make it in 2010, then in 2010 all the bars will be double the size of the 1960, because the counts have doubled. But this is not the right picture that we want. So this is so the correct picture comes from the probability histogram. There's only one minor difference between the probability histogram and the count histogram. In the probability histogram, we take the number of countries and we divide by the total number of countries. That's all. So the two pictures look exactly the same. It's only the markings on the y-axis which are different. When you have a probability histogram, then it always goes from 0 to 1, because the largest possible value is 100%. And in each bin, you have not the number of countries, but the percentage of countries. So if there are 90 countries in one bin, it is not the number, but 90 divided by 240, if 240 is the total number of countries. So each bin, the size of the histogram is the probability. Now when you put the probability, then if the number of countries changes, it doesn't matter, the graph remains comparable, because the percentage of countries in that bin matters. So now we go to the second concept, and that is called a theoretical distribution. So you have already studied the theoretical distributions. You know about the binomial distribution and the normal distribution. So I am going to illustrate these in Excel. First of all, there's the binomial distribution, which I am going to look at. So the binomial distribution has this structure, which I am just going to review. So if we have random draws from a population, and each draw takes value 0 or 1, then there is a 0 is called failure and 1 is called success, and you have to have independence in the random draws, and you have to have the same probability. Every time you draw, the probability of success should be the same, which is called P. And if you take n such random draws and you add them all up, you have a binomial distribution with n draws and success probability P. And in this situation, it is known that the probability that of k successes is n choose k, p to the k, 1 minus p to the n minus k, and this formula is also explained in detail in my introstat lectures. Now I am going to give an example of this. Consider suppose I want to, I think I've done this here. Yeah. Okay, what I have done here is that I have taken the GDP data, which is over here. So this is the country Zaire, which is the poorest country in the world in 2010. It has a GNP per capita of 105. Then there's BDI, I don't know what that stands for. Eritrea is 146, and so on. So the countries have been sorted according to the GDP. And now I am looking at an event, and my event is yes. What is my event? My event is that what I'm going to do is to take a random sample. I'm going to pick one country at random from out of the 246 countries, and I'm going to ask, does this have GDP less than 1,000 or bigger than 1,000? So if it is less than 1,000, I will count it as a success. And if it is bigger than 1,000, I will count it as 0. Since there is no country which is exactly 1,000, so it doesn't matter whether I choose less than or equal to or strictly less than. So these are not going to matter. So now, what is the probability of a success? Well, we look at the data. If you see the data, Ukraine has income of 1036, and Uzbekistan has 941, and that's the last country. So how many countries have income less than 1,000? 60, yeah, because the top line is. And how many total countries? That's 211, right? BMU, what is BMU? I think it's Bahrain. Yeah, I think it's probably Bahrain, but I'm not sure. I could look it up in the previous sheet, they have their full names. So, the probability of a success is equal to 60 divided by 211 is 28.4%, right? So now what I have done is I have chosen countries at random. I'm just illustrating some. Achha, ye main kya kar raha hu? I've forgotten what I did here. Okay. Right, now I remember what I did. Okay, so what I did was that what I want to do is I want to select a country at random and then check whether or not this has income bigger than 1,000. Alright, so actually in the exercise I did it directly. I chose one country at random. How can I choose a country at random? Well, each country is indexed at some integer. So 2 is Zaire, 3 is BDI, 4 is Eritrea. So if I choose one integer between 2 and 240 or whatever, how many, 211 I think, countries. So then, so I choose an integer at random from these values. So I can show you how to do this. Equals rand between 2 and 211. So this rand between is a Excel function which chooses an integer between 2 and 211, and so this is 45. So the first random choice was country number 45. Country number 45 is less than 60, so this means that this country has income less than 1,000. So it means that I have recorded a 1, a success. Now, so actually every time you do this, the rand between is a number which recomputes the random. So the next time it did it, it chose country 8. Again, this is a 1 because it says less than 1,000. Now it chose 209, so it's a 0. Now, because it's this country, 171 is above 61. 61 is the country at which you get 1,000. So 171 means that this is also a 0. 124 this is also a 0. So in this way, I can start choosing, and these are all binomial trials. And now what I want to know is, so what we are going to do is to take a random sample of, let's say, 100 countries, and then I'm going to ask, I'm going to delete this. Okay, so I'm going to take a random sample of 100 countries, and then I'm going to convert that to a binomial random variable, and I want to know what is the distribution of this random variable. So now 100 जो है वो जरा ज़्यादा हो जाएगा, yeah, okay. So let's try for a random sample of size 10. So now, okay. So now what I'm going to do is do two things. I want to show the empirical distribution and the theoretical distribution. Now, when you have a random variable, there are these two distributions which are coming into play. One is the empirical distribution. This is what you actually get. And one is the theoretical distribution, which is the probabilities which you are supposed to get. And these two are always different. And understanding the difference between these two is very crucial to understanding all of statistics and probability. So now what we are going to show is, okay, so I'm going to generate the actual data. So what I'm going to do to get, data analysis, random number generation, okay. Now, number of random variables, I'm going to choose 1. For the number of integers, okay. So now how many? Okay, here I'm going to allow for 100. The distribution is going to be binomial The p value is 28.4%, 0.284. That's the success probability. Number of trials is 10. And I'm going to ask for an output range. And I'm going to put this in K1. Okay. So now, this set of numbers, what is it? First you have to understand what it is. In column K1, I have this number 5. What does this number represent? This is a binomial trial in which I picked 10 countries at random. For each country I asked, is this less than 1,000 or is it more? And for each country less than 1,000, I recorded a 1. In this first trial, I found 5 countries which had less than 1,000, which is unusual. Actually, the probability is only 28%. But in this particular case, I happened to choose, because this is the main thing, the random variable is random. So it doesn't always come out the same thing. So in this particular case, 5 countries were poor. Let's say, to simplify our talk, that if a country has less than 1,000 GNP, it's poor country, and more than 1,000, it's not poor. Hard to call it rich, but anyway. So poor or not poor. So in the first trial, I chose a random sample of 10 countries, and I got 5 poor countries. The second time I did this, I got only 2 poor countries. The third time, I got 3 poor countries. Now, basically, between 2 and 3 is the average number. Yani 2.28% means that in 10, you should get on the average 2.8 countries. Of course, you will never get 2.8. You will get either 2 or 3. So, most of the time, you should get 3. Sometimes you should get 2. This is the average. But here, we are saying we got 5 once, then 2, then 3, then 1 and 1, and then 4, and then 2, and so on. So now, what I want to do is to show you the theoretical distribution of this data and the empirical distribution, just to understand what these concepts are. So as far as the theoretical distribution goes, that is given by the binomial distribution. And for the... Okay, so let me just make a table here. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. These are the 10 possible values. These are all. So I'm making a histogram, but here I have no problem with the bin size because there are only 10 possible values. So I just choose each bin has only one category. And now, first of all, I'm going to ask, what is the probability of 0? You see, technically, I can get, once I make a sample, I can get 0 countries which are poor, I can get 1, all the way up to 10. Each of these events has a probability, and the probability is given by the binom dist function. So this is binom dist. And now, what is the number of trials? Well, I want 0 here, comma. Now, what is the total number of trials? That's 10. The probability is 28.4. ये मैंने क्या डाला था उसमें? जब मैंने 28.7 तो नहीं डाल दिया था? 0.284, comma. Now the last argument says, is this the cumulative or the mass function? So I'm going to put 0. Okay, so this thing is telling me that the probability of 0 is 3%. The probability of 1 is 4%. 14%. Probability of 2 is 25%. Probability of 3 is 26.5%, and so on. These are the theoretical probabilities. Now what I am going to do next is to calculate the actual data frequencies. So I am going to enter here equals. Now there is a function called COUNTIF, and COUNTIF I am going to put in here K1 to K100. These are my 100 random variables, comma, and what is the criteria? I want to put less than 1000, and hopefully this will work. Okay, what? Oh, acha. No. I don't want to put less than 1000. That's in the countries. Now here I just want to count the zeros. Equal to 0. Okay. So, how many countries had 0? How many times in this 100 rows, how many times did we get 0 poor countries? All 10 countries were rich. Well, this Excel function is telling us that there were 2 times. We can actually go and check here if we want to. 100 is not that large. There's 1 0, and there's the other 0. So you see, the COUNTIF function does this for us. Otherwise we'd have to go and count by our fingers, but it's difficult. So now this is the theoretical distribution, and this is the observed or empirical. Sometimes it could be, actually we shouldn't call it the data distribution, because it's not data. This is the random variable. So this is called empirical distribution. So now the theory said that 3.5% of the time this event will happen, and actually the number of times it happened was 2. Now how about 1? We can do the same thing. Equals count if. What I'm going to do is put dollars in here. $K $1 colon $K $100 comma equals oh my goodness, equals 1. Chalo. Okay, so there were 11 countries which had this. Now what I need to do is to change this. There is a way to do this correctly, but I have forgotten. So now there were 25 countries. Let me try it this time. Maybe this will work, I'm not sure. And N6. Yep, no, that didn't work. No, that didn't work either. Anyway, so we will go to use the method that I know. Okay, so this is looking at the observations and counting how many of them are equal to 3. There's an extra. Okay, so there are 35 of them. This is much bigger than the 26% probability. And so on. Wish I could do this quickly. Okay, so this is 4. The theoretical probability was 18% and 18.4%, and the number of countries which actually number of trials in which we had 4 poor countries was only 13. Then we had 11 countries which had 5 poor countries and 5 rich countries. The theoretical probability was 8.7% or 8.8%. And for 6 we have 2. And okay, I'm going to just shortcut this by putting zeros, even though this is not correct. Okay, because I want to show something about this, and what I want to show is the graph of the histograms. Okay, I'm going to take this, and now I'm going to try to plot a graph of this. Okay, what happened here? Oh, अच्छा, ये दोनों comparable नहीं है, क्योंकि what I want to do is to change this into you see, that's the, on one side I had the count histogram, and the other I had the probability histogram, and these two were not comparable. So what I need to do is to take the number of countries in the bin and divide it by the total number of countries. So if there are 2 countries, I divide it by 100, which is the total number of countries, and now I get the right histogram. And now you see, now these numbers are comparable. And now I want to draw the graph. Okay, insert. Okay, now we have what I wanted to show you. The blue graph is series 1. That's, you see, nice and symmetric. That's the binomial true probabilities. The red graph is the histogram of the actual observations, which is different, which is random, which is irregular. It can behave differently. Every time you do this experiment, the red graph will be different. The theoretical graph, the blue graph, will remain exactly the same. But the random variable, if you draw a new random sample, you will get new probabilities, different kinds of probabilities in the bins. This particular time, the 4 came up much more. It came up about 35% of the time, even though the theoretical probability was only 28%. So next time you do it, it might come up 20% or 15%. So the red graph is the observed or the empirical histogram, is the empirical distribution also, and the blue one is the theoretical distribution. So now we have 3 different types of distributions, concepts. One is the data distribution. Then data distribution has nothing to do with randomness. It's just, if you look at the data, you divide it into bins and you count, or you take the proportion. If you count, you get the count histogram. If you take the proportion, you get the probability histogram. Then we look at theoretical random variables. For each random variable, you have the probability that it will be in any bin, and that can be calculated like in the binomial. Similarly, for the normal distribution, we can also calculate the probability, and then we can get the okay, let me do the normal case just to show how it works. So now I'm going to show how to do for the normal distribution. I'm just going to open a new sheet. Okay, first thing I want to do is to create normal random variables. That can be done by looking at data, and we go to, what happened? ये data analysis कहाँ गायब हो गया? हाँ? क्या हो गया? Side पे? I can't see it. Validation अभी तो था हमारे पास. Let me go back to the other sheet. Have we lost data analysis? Formulas? What is going on? Maybe I have to add it in again. Options, add-ins, analysis toolpack, go. Magar, where is it? Okay. Left है. आमना ये डेटा एनालिसिस कहाँ गायब हो गया यहाँ पे? एडिंस में चले जाए. बंद रहती सिलेंडर को दोबारा खोलते हैं. ये ऊपर से बंद करना. नहीं वाली स्टार्ट से बंद से खोल देते हैं. अच्छा चलो. अच्छा कहाँ यहाँ से? चलो एक क्लिक अच्छी जी आएगी. हाँ आ गया फिर से. पिछली बार वो ये गायब हो गया था. सिर्फ सॉल्वर था इसी बार में. Alright, so now what I'm going to do is go to random number generation. Okay, I'm going to choose one variable, and let me try a bigger sample size, 1000 this time. and normal random variable, and now it chooses the mean 0 and 1 default, and I'm going to let it go like that, but I'm going to choose the output range to be from A1. Now it's going to create 1000 random variables. Okay, these are my 1000 random variables. Now I'm going to plot them, both the theoretical and the empirical distribution. So first I'm going to give my bin size minus 2.5 minus 2.0 Okay, so I've chosen bins from minus 2.5 to plus 2.5. There's a reason for this. I mean, why did I choose these? Well, you see, if you look at equals norm S dist. So this is norm. There's a normal distribution which is norm dist. Norm S dist is normal standard distribution. Norm S dist of C2 is 0.0621. So the probability of something being less than minus 2.5 is about 0.006, which is 6 in 1000. So in this whole data set we will have about 6 observations which are under 2.5. That's the theoretical expectation. Now the norm dist gives you the probability of being less than or equal to. Now to get the bin size, which is what we want, here we can just take 0.00621, because that's the bin size, anything less than or equal to. But in the next bin from minus 2, what we need to do is we need to take this number and then subtract from this the previous number. See, that's 1654. So now between minus 2.5 and minus 2, we should have about 1.6% of the data. So about 16 observations should be in there. And now I can make a histogram. So this is the theoretical histogram. Now what I can do is make the empirical histogram. These are the probabilities of a normal variable following. One thing that is important to note is that the normal distribution is very well behaved distribution. It doesn't have outliers. This is another major reason why standard regression analysis and standard data analysis fails very badly in real data sets, because the assumption of normality means that there are no outliers. So the assumption, so the data analysis is done under the assumption that there will be no outliers, and most data has outliers. So this is something to understand here, because what I want to show. Okay, I'll show it like this. I'll go to home, sort, custom sort. Okay, column A, by values, smallest to largest. Okay, so you see the smallest value is minus 3.0 and the largest value is 2.98. So basically in 1000 variables we have the range is between minus 3 and plus 3. which is about according to the theoretical probabilities. No outliers. Now, suppose I want to show you what happens if we take, instead of normal is very well behaved variable without any outliers, ratio of normals is a very badly behaved variable. So what I'm going to do is I'm going to take this one and divide by the previous one. So this is just the ratio of two normals, 0.98 here. Oh, what's going on? ओ अच्छा अच्छा, ये इसलिए हुआ कि मैंने इसको सॉर्ट कर दिया है. ओए होए, अच्छा, because it's sorted, so there is no bad variables. Can we undo the sort, or shall I just generate new variables? Let's go here. Okay, I'm going to just do this one more time, and I'm going to just change the output to okay, these are our normal random variables. Now I'm going to so this is the ratio of the first normal to the second normal to the first, and by copying this I will get okay. So you see this random variable, which is the ratio, is not very well behaved. It's 0.16, then minus 12. Just going to let's look at these numbers. These are all good numbers: 1.6, 2.78, 2.5, minus 5. Everything is reasonable. Minus 3 is a big number here, but okay, minus 6.97, minus 22. You see, this is the thing that happens. Now, if you look at, this is the 37th observation. Now, if you look at the first 36 observations, they are all between, there is a minus 7 over here, and a minus 12. So, if one looked at the first 36 observations, you would say that, okay, so minus 12 is the smallest observation, and I don't know what's happening on the big side, but maybe 3 or 4 is the largest observation. So based on 36 observation, well, you say that, okay, the smallest possible is minus 12, and the biggest possible is maybe 5. So on the basis of that, you would never believe, okay, the next one could be minus 22. Right? Because it doesn't match with your experience. This is exactly the problem with the normal distribution. Normal distribution is a very smooth and simple and stable distribution. It's predictable. But some distributions are unpredictable. This distribution, the ratio of normal, is unpredictable. Your experience will not tell you what's going to happen next. This is called the black swan theory. So basically, basically all of the standard theory is built on the idea that the distribution that you're going to see will be normal, and that's why the normal theory is wrong. Now what I was going to do, let me go back to the slides and see if I have done something like that. Okay, so we made a theoretical distribution, then we drew a random sample, and then we compared the theoretical with the empirical, and we saw that there is a discrepancy. This discrepancy becomes smaller as the sample size becomes larger. The same thing true in the normal distribution. If I draw a sample of size 1000, it will be a fairly good match to the theoretical probabilities. If I make it 10,000, it will become an even better match, and so on. The last thing which is very important is that Now the relationship between the data distribution, if I take a random sample from the data, then I ask, in the original data, in the first bin there are 4 countries, let's suppose. So, and out of a total of 211. So if I take a random country, what is the probability that it is in the first bin? Well, it will be exactly 4 over 211. So when I take a random sample, its theoretical distribution is the same as the data distribution. The actual distribution will be different, the empirical distribution, because if I take a random sample, it's not necessarily true that 4% or whatever percent will fall into a given bin. It can be larger or it can be smaller according to random variation. The theoretical distribution is the same as the original true data distribution. The empirical distribution is different. It's random. As the sample size increases, the sample distribution or the empirical distribution converges to the data distribution. This is the most fundamental principle of statistics. So to illustrate, I need to give the example. Suppose I want to know what is the distribution of heights in Pakistan, or the distribution of income in Pakistan. So what I do in the HIS, I have a random sample. Now, the true population distribution, the data distribution, would be obtained like this. I would take the interval 0 to 1000 and I would count all of the people in Pakistan who have income between 0 and 1000. And there is some number, but actually nobody knows what that number is, but there is some number. Let's say it's 6 million or something like that. So, okay, so my count histogram would have 6 million, and my probability histogram would have 6 million divided by the total population of Pakistan in the first bin, 0 to 1000, which will be some probability. Let's say it's 10%. Okay. Now, if I take a random sample, and in the highest income distribution, I have a random sample. I have 15,500 households which were chosen at random from Pakistan. So what is the probability? So I count how many households in HIS data have income between 0 and 1000. And let's suppose that it is 1000. So I have 1000 households in HIS which have income between 0 and 1000. I can count it, but I don't want to take the time to go to Excel and count. So what is the probability? So the count histogram has 1000 households in the range 0 to 1000. What is the probability of being in 0 to 1000? It is going to be 1000 divided by 15,500. That's the total number of households in the sample. So now this 1000 over 15,500, that's the probability in the first bin. This should be close to the true probability, which is the probability in the population. But actually, in this case, we don't know what the true probability is. In the case of the countries, I knew what the true probability is. In the case of the binomial distribution, I know what the true probability is. In the case of the normal, I know I can calculate. But in the case of the real world population sampling, I have the observation, I have the random sample, I have the empirical distribution, I don't have the true distribution. But I know there exists a true distribution, and I know that the true distribution is close to the random. So I can guess that maybe, and if I want to guess what is the true number of people in Pakistan which have income between 0 and 1000, I look at the proportion in my sample and I multiply it by the population of Pakistan, and I have an estimate of the true, because the true distribution in Pakistan should match roughly the distribution in the sample. That's the basic idea. So the data distribution, which is the true distribution of incomes in Pakistan, is going to match the highest sample distribution, which is the random sample of 15,500. How closely they match? we cannot tell. If I take the random sample again, we will get some other fluctuation, but the true distribution will not change. So basically the process of statistical inference goes like this, that we take the random sample and then we assume that this should be close to the population, and sometimes we are lucky and it's right, and sometimes we are unlucky and it's wrong. And that's basically what we showed in the Excel, that the red bars and the blue bars, the theoretical and the empirical, are different, and how different they are you can see. And one more thing that I didn't show, I was going to show but it would have taken some time, is that as you increase the sample size, the convergence happens, that the random sample proportions converge and they become closer and closer to the theoretical ones. Okay, so that's all for this. Now there is an exercise which is ready and available. I don't know that. I think it's this one. Yes. Yes, this is the exercise, L02 data distributions. So it's now your job to get this file somehow or the other, and then to do it. It's a set of exercises. It starts by saying that L2 data file ले लें आप, और फिर save this spreadsheet, and then examine the numbers and so on. All of these things are, you have a list of things which you have to do with the data. Basically, there is nothing new. Everything that I showed in this lecture, this is what you have to do on your own. If you do it on your own, then you will understand what I was doing. Otherwise, you only have a vague idea. You have a rough idea of maybe what I was saying. But after you do it yourself, then you will have a very good idea. So there are these two files you need, L2 data distributions and L2 data, the Excel file. And with those two files, then you can do the exercise, and you have to get this done on your own by Friday. And then after that, you will, on Friday, Amna will help you. If in the middle of the, if while you are doing it, you can't figure out what's going on, then you can ask Amna